Hey guys, I wanted to point out a couple things while you're working through those problems that I assigned, and it's on your equation sheet. So your formula sheet, we did all of this stuff here, and now we're looking down in this area right here. So there's your kinematic equations for one-dimensional motion and see two-dimensional motion. So we have all of these equations that deal with two-dimensional motion. So I wanted to talk about these equations and what they mean and how you might be able to use them. So I've copied them over so that I can talk about them while I write. These equations, all of these, come from your kinematic equations. But it's actually pretty nice that they gave this to you. So I didn't give these to students before. They would have to know what to do. So let's go through each of these in turn and see what they mean. So the first one, it's labeled Freefall. And so this is just the kinematic equation that applies for freefall. Remember, freefall is either way. So if I'm going up and slowing down and then coming over and falling back down, and anywhere within this motion, this equation applies in the y direction. So it comes from this kinematic equation. Sorry, let me change it all to y's. So y is y naught plus vy naught t plus 1/2 of the acceleration times time squared. But in free fall motion, that acceleration is equal to g, which is down, and so that's why we get this negative over here. So changing this all, you get y is going to be y naught plus vy naught t minus 1/2 g t squared. And so this will give us our vertical position for a projectile. It'll tell us where it is along that, as long as I know the time, or I could find the time, or whatever it may be. Okay, so then we go to this next piece, and it says the velocity of the x is the initial velocity of the x. So what this is saying is just that it's constant velocity in the x direction. So for projectile motion, remember that the velocity at any point in time in the x direction is equal to whatever the initial velocity was. I write it like that, but it's the same thing, that initial in the x direction. So it's just saying that the velocity doesn't change. It's the same in the x direction. And because it doesn't change, we get this one. So that one comes from your kinematic. X is x naught plus v x naught t plus 1/2 of the acceleration in the x direction t squared. But we just said it's constant there's no acceleration. So this term goes away. And then if I move this over, if I move this x naught over, I get x minus x naught is equal to v x naught t. So that is the change in position is equal to v x naught t. So that's this equation. So this is what you did in class. You figured out the time, and then you multiplied by that initial velocity in the x direction, and that told you how far it went in the x. Okay, so now this one, it comes from the trig. So that's this equation, and then we just substitute the trig in there. So let's pull it out. So if I have an object that's launched with velocity v naught at some angle theta, then this portion right here, this vx, the vx is going to be, it's next to the angle, so vx is going to be v cosine theta. And then we take this quantity and we're going to substitute it back in here. So we get the change in position is going to be v cosine theta times t. And that's this equation here. And then this one right here, this is the velocity in the y direction. So the velocity in the y direction it comes from this kinematic. V is v naught plus the acceleration times time. And in our case, the acceleration for free fall motion is negative g. So we get v final is going to be vy naught minus gt. So again, everything comes from kinematics. Okay, now let's get into these. So what about the change in the height? So as the thing is moving, where is it? How much did it change its height, its vertical position? And so we get this one. Well, this one is just this rearranged. So if I go back, I'm going to take that equation. So y equals y naught plus vy naught t minus 1/2 gt squared. Now we just move this over, so you get y minus y naught, and that's your delta y. So vy naught t minus 1/2 gt squared. So this is delta y equals all of that. So that's this equation. So this one comes from this one up here. These are actually the same equation. And now we're going to substitute. So just like we did here, from v naught in the x to in terms of v. So going back to our picture, this little piece over here, that's vy. Since it's opposite, vy is equal to v sine theta. So now we can take that and substitute it in here. So we get v naught sine theta times t minus 1/2 gt squared. And that will tell me how high it is, or whatever. You know, you can solve for other things. That's where this equation comes from. And then we get to this one. This one is going to be your squared function, it looks like. I don't think I've ever derived this equation. So yeah, vf squared is v naught squared plus 2 times the acceleration times delta x. That's the kinematic, but this is all in terms of y. So if we want to know the velocity or the y velocity, you know, how much velocity does it have going up, then vy squared is vy naught squared. Then the acceleration is still negative g, 2g delta y. Now this piece right here, this vy naught, is v sine theta. So v sine theta squared minus 2g delta y. So this right here, we have to square everything inside of it. Equals v squared. And then sine theta squared, we write it as sine squared theta. Don't put the square on the theta. We're squaring the function sine. Minus 2g delta y. That wasn't bad. So that's your third one. That's this one. The last one is your range equation. This one will be useful in the problems. I know number one, you could probably apply it pretty directly. So the range equation, I'm trying to think. Yeah. Let me see if I can derive it. This just tells me like how far it's going to go based on the angle and the initial velocity. So let's see, x, it's going to be x naught plus vx naught t plus 1/2 of the acceleration t squared, but there's no acceleration in the x direction. So we're going to get, if I move that over, we get delta x is going to be vx naught t. But suppose I don't know the time. Well, we can go ahead and just do this. Delta, it's going to be v, and this is cosine theta times t. Okay, so I don't know the time. So let's go over to the y direction and we'll solve for time. So y equals y naught plus vy naught t minus 1/2 gt squared. That's just your kinematic. And do I want to solve for time? This is going to be delta y is vy naught t minus 1/2 gt squared. Let me see. Hold on, because I was working on this. Hold on. Because it's a quadratic, it's going to get messy. Let me see what happens. So it's going to be v sine theta times time minus 1/2 gt squared. What I'm thinking is, you know, here's what I'm going to do. So I was going to solve for time here, but this is quadratic. But this time over here is linear. Sorry, hold on. I need to close these windows. It's slowing down my computer. Okay, so this is linear, so we want to eliminate time. That's the idea, is to get the range. So time in this case is going to be delta x, my range, over v cosine theta. Now I'm going to take this and substitute it in there to get rid of the t's. So delta y is going to be v sine theta times t, which is delta x over v cosine theta, minus 1/2 of g times t, the delta x over v cosine theta squared. I feel like I'm going to have a y left. Was there a y in your range equation? Yeah, we'll figure it out. Okay. Okay, so change in position. Yeah, this range equation, you'll see it's only for when it hits the ground, leaves the ground and hits the ground at the same height. So let's start simplifying. Delta y is going to be v. The v's right here are going to cancel when we multiply. And then, so we get delta x sine theta over cosine theta. All I did was pull the x out in front and then move that in. So we're just multiplying it across. I'm just rewriting it like that because this right here is tangent. I'll explain that in just a second. So minus 1/2 of g. Now we got to square everything inside. What was that? Oh, that's delta x. I didn't write the x. Okay, so inside we get delta x squared over v squared cosine squared theta. Okay, let's deal with this. So remember that sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. So sine over cosine theta is going to be opposite over hypotenuse divided by adjacent over hypotenuse. And we can simplify this fraction by multiplying the outside. So on top you get opposite hypotenuse, and on the inside you get adjacent hypotenuse. Those cancel. So sine over cosine is opposite over adjacent, which is tangent theta. So now we can do delta y is going to be delta x tangent theta minus 1/2 g delta x squared over v squared cosine squared theta. And what I want to do is I want to get these delta x's together, but dang it, I got a quadratic again. So what we would have to do at this case, so this right here, this would be like if you launch it and it lands up on a like a cliff, or you launch it from a cliff and it lands down below. If it goes from here and lands here, then the delta y equals 0. So then we can solve this. So this is 0 is equal to, I'm going to flip this around, tan theta delta x minus 1/2 g. I'm going to move this a little bit. So let me rearrange this a little bit. This is going to be g over 2v squared cosine squared theta times delta x squared. Okay. So now I can factor delta x. So I got tan theta minus g over 2v squared cosine squared theta times delta x times delta x. So what this is going to answer is, when is the change in position 0? Well, it's here is one of them. So delta x equals 0. This one equals 0. And then I'll do this one. So I get tan theta minus g over 2v squared cosine squared theta delta x equals 0. Now I'll move this term over. So we get, this is going to become negative, so then I'll have a negative and negative, so it all becomes positive. G 2v squared cosine squared theta delta x equals tan theta. To get my range, now I'll flip this and multiply by the other side. So delta x equals tan theta, or it's going to be 2v squared cosine squared theta, because it's going to be multiplied up on top, times tangent theta divided by g. That's not the equation they had. Oh, man. Let's see. What did they have? Sine squared, v squared. So we got we have our v squared over g. It's that sine 2 theta. It's going to be this cosine squared times sine squared. So let's look at that. That's going to be delta x is equal to 2v naught squared cosine squared theta. Tangent is sine over cosine. So this is sine over cosine theta over g. So delta x, you can see this cosine is going to cancel one of those. So we get 2v naught squared cosine theta sine theta over g. And this right here is a trig identity, cosine times sine. That's how we get that, that last term, the sine of 2 theta. So we're going to get delta x is 2 v naught squared sine of 2 theta over g. I think that's how they wrote it, right? Or no, what happened to that 2? Oh, I'm sorry. The trig identity, this goes away. 2 times cosine sine. Let me show you so that you believe me on this. Okay, so I pulled up this trig identities and we were looking for cosine sine. There it is. So right here. 2 times sine cosine is sine of 2 times that angle. So that's where this this last little step came into. 2 times cosine sine is sine of 2 theta, so that's your range equation. You don't need to know the derivation. I just wanted to walk you through it, and actually that one was really messy. I just wanted you to know that it all comes from kinematics. So usually in the past when I've taught physics, they only learn 3 equations. Everything else is derived. So they always hated this range equation. So anyway, I wanted to point that out on the equation sheet. Use these if you can. So there you go.